Something like 15 minutes to hear the satellite while it overpasses your location. And in order to listen to satellites, we use ground stations. As you can see in the picture, this is a big and scary one. It's from it's one from European Space Agency. But ground stations can be down to hobbyist ground stations and those that use ham operators. And a ground station is basically an antenna antennas mounted on top of a rotator. And the rotator can help us move the antennas and point to a position in the sky and track that object, and also listen to the frequency that this object transmits signals. As you can see in the picture, ground stations can be super expensive, and also they might be heavily regulated in some cases. So in order to tackle the problem that we're facing is that we initially wanted to have an open source reference design that is going to be cheap enough and it's going to use materials that anyone can source, and practically we wanted anyone with some basic knowledge to be able to build a ground station. But that is the first part that we need to solve. The most interesting part for us is that due to the sort of repassing window that you have to communicate with satellites, the communication cannot be synchronous. It has to be async. And that's what we also want to tackle, the global coverage. So the idea is to create a network, which sounds easy, right? And the initial design looks something like this in the chart. We wanted everyone interested in satellites to be able to have access to a global management network that can handle observation tasks. Anyone with that kind of access could tell which satellite he wants to track, and using our network, he's able to send tasks to ground stations distributed around the world, and then listen to satellites, and then the data get posted back to the network so anyone can reach it. When we came up with the initial architecture, we found out that there was no unified way to do this, so we decided to do everything from scratch. But this sounds difficult, so we wanted this to be as modular as we can, so we can use existing components and an existing technology to solve the initial problem. So let's dive into our stack. First comes the rotator. As you can see in the picture, this is our third iteration of our design. Practically, a rotator is a mechanical device that enables antennas to move on azimuth and altitude dimensions. And this is our last design, and we wanted this to be easily built. We wanted this to be 3D printed, so any hackerspace with prototyping tools could build it. And we also wanted this to be cheap, so everyone can have access to it. And on top of that, we didn't want to create something that has worse specs than what other rotators have in the market. So our rotator, our design was initially to be as reliable as the rest of the operators in the market. Here's the picture of our previous version. This is V2 SatNOGS. This is the deployment that we have in Hackerspace in Athens. It's mounted with a helical UHF antenna, and we have already been using that for some time. For the receiving part, we are using everyone's favorite DVB-T. The off-the-shelf solution caused some instabilities, so specifically we had some problems with the PPM errors, so we decided to go with the modded ones that you can find in the market, and with the patched oscillator, so you can have more stable product. A ground station can be permanent and portable, and we have designs for both. We want both permanent and portable deployments. We provide designs for a tripod, so anyone can have a portable design. But for those that want a more permanent setup, we also have designs for a dome, which is optional, but is very useful in some cases with extreme weather conditions. But yeah. So the most critical part, our center part of our design, is the network. The network is where all the data get gathered, and when someone wants to track a satellite, he just has access to it and then submit an observation job, which gets populated to the distributed network of ground stations. We wanted this to be as open as possible because we strongly believe in open data, and we want our observations to be accessible by anyone who wants to do experiments or use it for any other project. So here's a screencast from our network. Here you can see a list of observations already submitted, and we are about to do a new observation. We select a satellite, for this case FineCube, and we also select which transceiver that we want to listen to. And also we also define the start and end of the observation time. Here you can see we can fine-tune it. And then we tell the network to give us an observation, to schedule observations in our network. If that doesn't work, we can change the time frame and fine-tune it once again. And then, if that fits, we schedule the observation. Okay, so even if we have a scheduler for our ground stations, we need some software to run on the ground station side. This is SatNOGS client. We have built it in order to facilitate the needs of the computing needs of the ground station. So when an observation gets scheduled, ground stations poll the network and get the jobs that are assigned to each one. And when the time comes, the SatNOGS client tells the ground station to start tracking, and also moves the rotator and tunes the radio for a specific frequency, and also calculates Doppler shift. And for the time frame that the schedule lasts, it records what the satellites transmit. And also, when the observation ends, it sends back all the data to the network. SatNOGS client is built using Python. Basically, the team that started this project was comfortable with this language and also was a good fit. So everything is based on Python. And we are trying to use existing protocols because we believe interoperability is the key point for what we're doing. So what we're doing at this point is using rod control and rig control. Rod control is a protocol that enables us to connect with a rotator and send commands in order to move it. And rig control is the protocol that helps us connect with the radio and change the frequency, which is really useful for Doppler shift calculations. And also, we didn't want to build the software that does the software-defined radio from scratch, because it was practically impossible. So we use existing software such as RTL-SDR and Multimon, and we also use OGG for the encoding. And our design was initially built in order not just to facilitate our needs, but also use the client with other rotators and other deployments that are out there. So we wanted this to be as modular as it can be and as interoperable as it can be, because we believe that there are many setups out there that are underused and they are idle for a long time. So we wanted this in the network as well. An interesting issue that we encountered was that there was no source to get transceiver data. And by transceiver data, I mean information about satellite frequency and modulation and baud rate. And a description of how the satellite transmits signals. So we decided to use some community help, and we built SatNOGS-DB. SatNOGS-DB is a crowdsourced satellite transceiver database that aggregates information about transceiver data and has a more formal way to present it. It's built on top of Django, and we provide a public API for that in a typical manner because we believe that these data are useful for other people and other projects as well. So through the public API, anyone can get satellite transceiver data. And the reason that we believe that this was useful is that many community members were already gathering that kind of data in blogs and in web pages, but there was no way to have a central API or a representation in order to get more programmatically this kind of data. So this was really helpful from the community, and we believe that this is successful because many people have already submitted their information, and it is already being used by other satellite enthusiasts. So overall, our stack looks like this. You can see in the right, we have different combinations of antennas. For example, you can use UHF, VHF, Yagi, or helical, and whatever you actually want practically. And you can mount it on top of SatNOGS in a reference design, but we make it easy for everyone to use their rotators as well. So anyone with a commercial rotator that supports the protocol that we're using can use their rotator in our network. So on the ground station side, you can use any embedded device you want and run the software, like Odroid or Bicklebone Black. And we have made it this way that we enable it for anyone to use whatever computing device they have in order to use the ground station. And on top of that, we have the software. We've built SatNOGS client, which is the part that moves the rotator and tunes the frequency, but there are many commercial software there that we as a community don't necessarily support, but you can use it. And there are also open source alternatives like gpredict and gqrx that you can use. Actually, gpredict is the equivalent of the rotator movement, and gqrx is the software that connects to the radio. Finally, you can either use the ground station like standalone offline, or you can be part of the global network and use it through the global management website that we have, and return data back, but you can also use it offline. As everyone understands, this is really complicated for a small team to build, so this wouldn't be possible to achieve without the help from the community. Here you can see some pictures of ground stations being built around the world. We have already four already built and connected to the network, and at the moment we have information that people are building it and send us that kind of pictures. So through mingling with the open space enthusiasts all around the world, it was clear that just satellite communication is not enough to advance our open source ideals. So we decided to create LibreSpace Foundation. LibreSpace Foundation is a non-profit initiative that we are aiming to advance Libre and open source space projects through this foundation. We already have some satellite-specific open source projects in the works, but we want more people to contribute to it, and we want to reach out to more satellite enthusiasts so we can collaborate on other projects. We've had some huge milestones by now. We have a working rotator, and the network works, and pretty much all the stack is in a working state. And we have some next steps so far. We want to add more ground stations in our network. We want to extend the coverage that we have, and we want more people to be able to use their rotators. And except of receiving, we are also planning to have transmitting capabilities. And lastly, we want to increase interoperability with existing systems. We know that there are many rotators and many setups out there that they're like academic projects and they're in an idle state, so we want them to use our network and reuse the available equipment. So we need you. All this project could not be possible without volunteers like us. So we are still looking for more people to join our project. Our stack is huge and we are looking for contributors from different backgrounds. So we need mechanical engineers and electrical engineers and RF experts. And practically anyone with an interest on space can reach out to us and see if there's something interesting to do. Thank you. You can check satnogs.org for more info, and you can also reach out to us in the Space Village when we have a SatNOGS deployment live. And for more information, you can check out the community forum where is the discussion going on, and our GitHub page where all the projects are there and they are documented. And for the deployment, you can see this. You can go to this URL network.satnogs.org and use our network. Thank you. Questions?
Wow, thank you very much. Are there any questions? Please come to the 2 microphones. Are there any questions? No? I don't get it. Yeah, please come to the microphone. No, please to the microphone, or the microphone goes to you, because it is recorded and the microphone has a cable.
Cannot hear.
Microphone, audio, guide, Angel.
Testing. Oh, hello. Hi, I was just wondering, what's the average cost of a deployment?
Right now, it's something like 300 to 500 euros, depending on which equipment you have available.
Thanks.
Next, please.
Hi, I just wanted to ask, I didn't understand the model of the flow of information. So do you request as a user so that other ground stations may track a satellite, or do you submit what you just collected on your own?
No, the idea is that we want users to define which time window they want to observe a satellite, and then use the ground stations available in our network that are connected to the network in order to schedule that and return the data back to the user.
Thank you.
Can you share with us some use cases? I know that there are weather satellites and other stuff, some interesting use cases of
yeah, so first of all, there is the initial need to communicate with the satellite. There are many amateur satellites there, and also people there launching CubeSats, and communicating with satellites right now is super expensive. And we wanted this to be available in an open way.
I know, but what kind of data we can expect in that kind of communication? Was of course, from weather satellites
So basically, the 2 main categories are status beacons, when you actually get the satellite status, and also you can get back the data from an experiment, let's say. So you need a way to run an experiment in a satellite, and then you need a way to get that data back. So the satellite can transmit the results of it, and you can receive it using SatNOGS.
Are there any more questions?
So what's the observable bandwidth, and what kind of signals or what kind of data do you get out of that? Is that demodulated stuff, or is it...
Sorry?
What kind of data, what kind of samples do you get? Do you get raw IQ, and also how broad is the observed bandwidth?
Yeah, so getting a raw IQ could be really big for the bandwidth that we have right now in terms of network. So what we provide is what we are planning to provide is, right now we are only providing OGG output like sound, and we are also aiming to be able to demodulate stuff on the ground station side, so it's going to be something like binary.
Yeah, you said audio, but I'm not a ham, I'm more a software-defined radio guy, so audio? What does audio imply here? Because there's RF wave coming in and not audio waves.
Sorry, I don't get the question.
You don't receive audio, you receive RF, so what kind of modulation is that maps?
It's actually it's only a frequency modulation, FM, and then that gets coded to
okay. That explains the OGG encoder. Okay. So there's no chance to get the raw signal that you receive right now?
Right now, no.
Oh, sad. Thanks.
Someone else is curious? Great. Come to the microphone.
Hi. Can you say something about the lifetime of the satellites currently? And secondly, who is in charge of coordination, like orbital control and coordination with commercial stuff up there?
I didn't hear the question. Could you please repeat it?
The lifetime, what's the lifetime of these satellites so far? And secondly, who is coordinating with other satellites out there?
So about the first one, I'm not sure what's the lifetime of a satellite, but right now we are trying to get in touch with other satellite enthusiasts in order to define some standards on how to cooperate with the rest of those interested. So there's not something formal right now. We are trying to reach out to other people interested. I'm not sure I got the question right.
Yeah, like what's the usable, like how long can they operate basically? You know, a cube, a satellite.
I'm not sure what's the time until it goes out of orbit. I'm not sure.
Depends on the experiment. Well, the second question was about the coordination, the orbital control, and like how is that handled with the commercial satellites?
I have no idea about commercial satellites.
No, I mean they use the same space basically. That's what I'm trying to get at.
I'm not sure I get the question. Sorry. We can discuss it after the presentation.
Are there any more questions? Okay. Thank you very much. Give him a warm applause for this interesting talk.